In this screencast, I'll be looking at the capacitance of a cylindrical capacitor. We're going to keep in mind our 4 steps that we've established in previous screencasts. The first one is to recognize that we have a charge of plus Q here on the inner solid conductor. The inner solid conductor has a radius of R sub A. And that we also have a corresponding negative charge on the outer surface of negative Q here, and the radius of the larger conductor will be R sub B. So now that we've established that, we have to solve for the electric field E. We're going to do that by using Gauss's law. We're going to establish a cylindrical Gaussian surface, and I've placed it in between. It's 3-dimensional, by the way, so it extends here into this kind of cylinder that could be something like a coaxial cable. And we're going to say that the electric flux is equal to the integral across the surface of the electric field dotted with the area vector, and that's going to be equal to Q enclosed over epsilon naught. This is Gauss's law. We're going to be using the middle pieces here. We're going to be ignoring flux, and we're just going to be looking here. And what we're going to say is that the electric field at the Gaussian surface is constant, so it's just going to be E, and the area is going to be equal to 2 pi r, where little r is the radius to the Gaussian surface, times L, the length of the Gaussian surface. So the circumference of the circle times the length of the cylinder is the surface area of the cylinder. And that's going to be equal to the charge Q, which is the plus Q that's enclosed by the solid cylinder, the inner solid cylinder, over epsilon naught. Now I can solve this for E. I am going to make a substitution. I am going to say that the cylinder has a linear charge density lambda of Q over L. So a certain amount of charge per unit length, and therefore I can say lambda times L is equal to Q, and that's going to get substituted here into the numerator of my expression. Let's go ahead and solve this for E. This becomes lambda times L over 2 pi RL. We can see the L drops out here, and I'm left with, oh, I forgot my epsilon naught. I'm left with lambda over 2 pi R epsilon naught. So this is my expression for the electric field inside the cylindrical capacitor. Step number 3 then is going to be to solve for the electric potential. That's going to be negative the integral of E dot ds. In this case, we'll use dr since we're talking about distance away from the center of the circle. Let's go ahead and make some appropriate substitutions. This becomes negative the integral of E, which is this, lambda over 2 pi r epsilon naught times dr. And the next thing that we're going to do, which I'll move to the next line, is we're going to pull out our constants and define our upper and lower limits of integration. I could do that up here as well. We're going to integrate from RA all the way to RB, from R equals RA to R equals RB. That's my upper and lower limit. The constants are lambda, 2 pi, and also epsilon naught, and I'm left with dr over r. That is actually being integrated between RA and RB. So the dr over r takes the form of du over u. So I'm going to write this off to the side. Du over u, when we integrate du over u, that's just the natural log of u. And so since we know this from calculus, we can apply it in this situation. This just becomes v is equal to lambda divided by 2 pi epsilon naught times the natural log of r evaluated between RA and RB. So when I do that, this becomes lambda over 2 pi epsilon naught times the natural log of RB minus the natural log of RA. Well, the natural log of RB minus the natural log of RA is just natural log of RB over RA. So let's go ahead and do that. This becomes V is equal to, let me go ahead and make one more substitution in for lambda. It's going to be Q over L. So basically, I'm substituting here into here. This becomes Q over 2 pi epsilon naught L times the natural log of RB over RA. It appears as though I have forgotten my minus sign. I've forgotten to carry it forward. So I'm going to add that into all of my work. And the reason is I now need to get rid of that minus sign. And I can do it by flipping RA and RB. So this becomes Q over 2 pi epsilon naught L times the natural log of RA divided by RB. And this is my expression now for voltage, or electric potential. And the last thing I need to do, which, since I don't have a ton of space, I'm going to do it over here. I'm going to say that capacitance is equal to Q over V. Well, in this case, Q divided by V, which is Q over 2 pi epsilon naught L times natural log, well, now wait a second here. I'm multiplying this is in the denominator, natural log RA over RB. And so the Q's cancel out, and my final expression looks like this. The capacitance for a cylindrical capacitor is 2 pi epsilon naught L, the length of the capacitor, divided by the natural log of RA over RB. And that is my expression for the capacitance of a cylindrical capacitor.